Jupiter played a crucial role in developing life on Earth. Thank you, Jupiter. We normally just see the very top layer of atmosphere. There are so many secrets of Jupiter contained below these clouds. So I'm currently analyzing data from the Juno spacecraft.
Juno, the spacecraft, has all these magical instruments to see inside of Jupiter. Jupiter is the most extreme environment NASA's ever visited. To send a spacecraft there is a little bit insane. This is one of the largest spacecraft ever made. We had to, build an armored tank to go there.
Jupiter's radiation environment is the most dangerous environment for a spacecraft to go into. It's a region we were very afraid of because no one had ever been there before.
If that doesn't fire just right, you fly right past Jupiter. That's it. You don't go into orbit, you go around the solar system again. By the time you come back to Jupiter, it's decades later.
Almost there.
It's a very uncomfortable situation.
Welcome to Jupiter.
We just did the hardest thing NASA's ever done.
What we actually found blew our minds. When you first look at Jupiter, what really catches your eye is the Great Red Spot. It's this gigantic storm in the southern hemisphere of Jupiter. It's larger than the Earth. It has been around for over 200 years, and it's absolutely incredible. Then you begin to look further away and you see these belts and zones moving in different directions on the planet, and everywhere you look, you basically see a storm. And what drives these storms? Well, likely Jupiter is collapsing very, very slowly. This is energy left from its formation, and this energy is released, and it's that energy that churns the atmosphere so violently all the time. This is in contrast to Earth, where our weather is governed by the sun. A lot of tourists go to northern Sweden and Scandinavia to see the northern lights of the Earth. If you really want to show and something that's on all the time, you go to Jupiter and see Jupiter's aurora. It's brighter than all the energy that all the power plants on Earth can produce, and is actually fueled by a volcano. So Jupiter has this moon called Io, and that's fiercely volcanic, spewing out material near Jupiter all the time, about a ton a second of material. This material gets trapped by the magnetic field as energy funnels down, impacting the planet, and that's the aurora we see.
What we find is vortices, kind of like hurricanes. They're all packed together, and we've been watching them now for a year, and they haven't all merged into one. They're packed in this pentagonal pattern. There's actually 6 of them if you count the one in the center. And they just sort of sit there, and this is remarkable. This is really the first time that anyone has seen such a geometric pattern of cyclones on any planet or anywhere. I look at an image like that and I say, wow. The idea that nature can make such a geometrical structure is fascinating.
We've known since the Voyager missions that lightning exists in the clouds of Jupiter. What Juno's found is there's a second form of lightning at Jupiter.
This is the signal from the microwave radiometer, and it's measuring the heat of the planet, and every now and then we get a spike. Bam! It became very clear very soon that this was radio signals from the lightning in Jupiter's atmosphere. Maybe 1,000 times brighter than the lightning on Earth.
The presence of lightning at Jupiter hints at vast amounts of water, and Juno's actually confirmed that in the lower part of the atmosphere, 1 out of 400 molecules is a water molecule. That's a lot of water. Does that mean that there's life in Jupiter's atmosphere? Well, ultimately, we don't know. We have this notion of what life is based on our experience here on Earth. Can we translate that to Jupiter? Can there be life forms floating about in the atmosphere? We don't really know. Jupiter is so massive, about 300 times more heavy than the Earth. And with all this gravitational power comes huge responsibilities. Jupiter originally flung water into the inner solar system, creating the conditions for life at Earth. So thank you, Jupiter. It also likely altered the orbit of an asteroid that killed the dinosaurs 65 million years ago. Jupiter's presence, gravitational presence, is absolutely everywhere.
This is the outline of Jupiter, and basically what we're seeing there are just the cloud tops. But what we want to know is what's inside Jupiter.
Before Juno, we believed that Jupiter would have a really small core onto which gas just stuck by gravitational forces. And what Juno has found is actually that Jupiter has got a really big core.
There's something denser. It's probably like 5-10 Earth masses. It's mostly made of rocks at very high pressures and temperatures. So that shows that Jupiter started its life as a rocky, icy world, and that it captured the gas that was around, the hydrogen and helium. And that formed a giant planet that's Jupiter now.
I first became interested in Jupiter when I was at college in Sweden. There was a telescope on the roof, and one night we got to see Jupiter with our own eyes, and it was absolutely extraordinary. A whole different world that I can see right there in the night sky. What would he think about me today? I think he'd be proud, ecstatic.
It has the biggest volcanic plumes that we know of, with exotic sulfurous compositions, the highest temperature lavas that we've detected. It's as hot as 1800 degrees Kelvin. So Io wins lots of awards for being extreme. Some of us love Io just for its own sake. But it's also a laboratory for understanding other planets, especially the terrestrial planets very early in their history. When they were hotter, they had more heat. This was a time when life first formed, when plate tectonics was getting going. We'd in many ways, studying very early Earth is like studying another planet. Understanding Io might teach us something fundamental. I'd like to understand that type of volcanic eruption without having one happen on Earth today. That would be unfortunate for all of us living here. Io, that's happening today. Very high fusion rate volcanism, more active than the most active volcanoes we usually have on Earth. And it changes our whole view of how planets work. For terrestrial planets like the Earth and Moon, our thinking is that it's kind of like the lifetime of a human being. When you're young, you're energetic and active, and then you get more quiescent and more quiescent, then you die. Boring. Well, these outer planet satellites are much more like the Hindu life cycle, where you can be reborn and go through all sorts of cycles of activity. So very different concept of how planets work. We have no shortage of unanswered questions and mysteries throughout the solar system and beyond. Right. Io is a little bit larger than Earth's moon. It's one of 4 large moons of Jupiter. It's the innermost of the 4 large moons. And 3 of these moons are in a resonance. So every time Ganymede orbits Jupiter once, Europa orbits twice, and Io orbits 4 times. This means that the distance to massive Jupiter is varying, and the whole moon changes its shape, where the surface of the moon rises and sinks as much as 100 meters. In case of Io, every 42 hours. That changing of shape, it's like bending a piece of metal back and forth. It heats it up. So we've proposed the Io Volcano Observer in the Discovery program. That's NASA's low-cost category of planetary mission. But this mission would make 10 close flybys of Io while orbiting Jupiter. It has a suite of instruments, and the tour is designed so that we fly by Io at just the right times and places. In order to measure the tidal gravity signature, we have to have pairs of identical flybys, one when Io is closest to Jupiter and one that's otherwise identical but when Io is furthest from Jupiter. So it sees the same signal except that this difference in range to Jupiter, which changes the shape of Io. That'll tell us really what's going on inside Io. Does it really have a magma ocean? And even if it has a magma ocean, what type of magma ocean? That's really, I think, the most fundamental thing. And we need to get a spacecraft that makes close flybys of Io at a minimum. Landing on Io and orbiting Io would be even better. You have to understand, though, Io is deep within the intense radiation of Jupiter. So Jupiter has a very powerful magnetosphere. So it's a very high radiation environment. So it's very tough on electronics. So, we're not going to explore Io the way we have Mars with these long-lived rovers on the surface unless we have a revolution in electronics and how to withstand the radiation. So fast flybys is the way around that for now. Get in there close, get a bunch of data, and get out of that radiation as fast as you can. There are volcanic plumes up to several hundred kilometers high, very spectacular, and that some of that material may be directly escape Io, but also that high radiation environment and those energetic particles interact and strip off material. If we're so close that we're flying through a lava fountain, that would obviously be bad for a spacecraft. We hope to fly through the upper parts of plumes where it's mostly gas and very small particles that are not hazardous. Of course, if you make a math error and impact Io, that would not be good unless it was intentional to dispose of the spacecraft at the end of the mission. And that is how we would plan to end it all after the mission is over. It would mean a great deal to me to see this mission go forward. Now, I'm not going to be the one leading the mission at Io. It has to be the next generation. You have to think in terms of multi-generations when you're dealing with the outer solar system, and especially when you have to spend a decade just to get the mission approved. So for me, though, that's all fine. I get it started, and then I enjoy life and enjoy watching others carry on. And I have no doubt that Io will surprise us. It's a very surprising place, and it's surprised every mission that's ever looked at it. The conventional thinking is that there's no way there's life on Io. It's too hot. Well, it's only hot over 1% of the surface. There are certainly places with better temperatures. It's also thought that there's no water. Well, we haven't detected water. But we didn't think there was water on the moon either for a long time until we got better measurements. So we might be surprised about that. And also, what kind of life are we talking about? The only thing we know how to talk about is life as we know it, which is carbon and water-based life. So if it's some other kind of life, then who knows? All bets are off. So it's the surprises that will be the most fun and the most significant.
This is one of the few places in our solar system where we have a good chance to look for life. There's evidence for a vast subsurface ocean below the icy crust of the moon. The amount of water that's suspected there is many times more than all the oceans together we have on Earth. On the poles, you're approaching minus 200 degrees Celsius. Icicles that could be several meters high might be present. And if you're very lucky, then you might just spot a plume erupting nearby, like an ice volcano that ejects material from the subsurface to enormous altitudes. On top of that, there's a good chance that there's an energy source at the bottom of the ocean, hydrothermal activity, that can support the emergence of life. That makes Europa outstanding. Europa Clipper is the first mission that goes to the outer solar system that has the exclusive goal to investigate the habitability of the body in the outer solar system. It will launch in October 24 and will arrive at Jupiter in April 2030, so it's 5.5 years for Europa Clipper. Jupiter has like about 70 moons, so the number increases like every year by a bit. But there are 4 moons that stand out. That are the so-called Galilean moons. The innermost is Io, then Europa, then Ganymede, and then Callisto. With the telescopic observations before the arrival of the first spacecraft, you could see that some of these moons are really, really bright. They reflect way more light than a rocky surface would. And so, for example, Europa and also Enceladus, they are one of the brightest objects. And so it was suspected already at that time that the surface might be composed of shiny, reflecting water ice. I mean, after the investigations of the Galileo spacecraft in the late 90s, Europa became a prime target in planetary science all over the solar system. Because with a huge subsurface ocean, with the spectrotidal thermal activity, that became the first place that could be habitable in our solar system besides maybe Mars. That immediately sparked proposals of missions to go back to Jupiter and specifically investigate Europa. I mean, if you are a planetary scientist, probably the most rewarding science goal is to see if a planetary body is habitable or actually inhabited. So Europa Clipper will stay in orbit around Jupiter, and in most of its revolutions, it will have a close flyby at Europa. And the flybys are arranged in a way that it's like a web in the end surrounding the moon, that you have in the end a good overview over almost the entire surface after these 50 flybys. During this close flybys, you get an idea of what is evaporating from the surface of Europa. And from that, of course, you learn about the makeup, the composition of the surface. And this is, of course, specifically true if there's plume and venting activity. That's what I really would put a smile on my face, if we could measure plume material that's connected to the subsurface ocean of Europa. The instrument called SUDA, the Surface Dust Analyzer, is the instrument I'm working on. It measures the composition of tiny grains that are surrounding Europa, mostly ice grains. And these grains are knocked off the surface by micrometeoroid impacts. With the SUDA instrument, we can sample these materials, and with that we get an idea about the surface composition. We could constrain what salts were there in the ocean, if there's an alkaline, neutral, or basic environment, if there's hydrothermal activity at the bottom of the ocean, what the organic chemistry inside the ocean has evolved to. Unfortunately, we currently only have one example of a planetary body or a moon where life exists. And so it's very difficult to speculate about the nature of life elsewhere. If we look for signs of life on an icy moon like Europa, it's probably the most straightforward to just look for simple forms of life. If there would be complex civilizations in these subsurface oceans, we probably would have known by now, right? But I know that at least for the life on Earth, the access to oxygen is important to develop complex life compared to simple monocellular life. So this is one of the big science questions that Europa Clipper wants to answer. Has Europa Ocean access to oxygen that is created on the surface? So is material from the surface cycling back down to the ocean? If yes, then oxygen might be available in the ocean, and this opens up the possibility for more complex life. And not just a single cell, but maybe fish-like complex life. Everything between one cell or no life or fish-like life, like complex organisms that might be even intelligent or not, nobody knows. It's really up in the air. I look very much forward to the launch. It will be launched on a Falcon Heavy that was decided only a few months ago. So one of Elon Musk's rockets. And I'm really much looking forward because I never saw a rocket launch in my life. I like to see it. But on the other hand, it'll make me nervous. So that's always a problem. If rockets have a chance, even the safest rockets have a chance of like a 1% or 2% that there's some failure, and then everything was in vain because all the development has been done. Most instruments have been crafted twice, that you have a spare. So I really hope that the launch will go well. So I think it's one of the most exciting missions there is, and I'm really glad that I can participate in these endeavors.
The northern lights on Jupiter are the most spectacular in our solar system. They're stunning, and they're bigger than our entire planet. They produce incredibly powerful flares that reach terawatts of power. That's more energy than you'd need to briefly supply all of human civilization. What causes them? Why do they seem to pulse like clockwork? To truly unlock Jupiter's mysteries, we needed a way to get closer to it than ever before.
Jupiter is the most extreme environment NASA's ever visited. To send a spacecraft there is a little bit insane. We had to, build an armored tank to go there.
Juno arrived in Jupiter's orbit in 2016. As it got closer, the auroras on Jupiter became so dramatic and active that astronomers said it was like Jupiter was putting on a fireworks display for Juno's arrival, which seems apt given the sheer scale of the spacecraft.
Behind me is the Juno spacecraft, basically life-size. It's an enormous spacecraft, close to 70 feet in diameter as it spins around and cartwheels through space. This is one of the largest spacecraft ever made.
Juno showed us more than we'd ever seen of Jupiter's auroras as they rippled over the planet's poles. The northern lights on Earth are caused by solar winds entering our atmosphere and interacting with the planet's magnetic field. Jupiter's magnetic field, also known as the magnetosphere, is 20,000 times stronger than the one here on Earth.
It extends all the way back to Saturn and perhaps further. And it's the biggest structure in the solar system next to the sun's magnetosphere.
That's one of the reasons Jupiter's auroras are so huge. These gigantic magnetic tentacles capture particles from across the solar system, thrusting them towards the planet's poles, creating this epic light show that never dies. But this is only part of the story. As well as photographing Jupiter's dazzling displays, Juno also began mapping Jupiter's core. And that's when things got interesting. Jupiter is a gas giant. It is full of loads of gas, especially hydrogen and helium. And when hydrogen is under extreme pressure, it acts in a really weird way. It becomes liquid metal. Liquid metal! Like at the core of Jupiter is an ocean of liquid metallic hydrogen. And using some of Juno's findings, physicists in California tried to recreate this extraordinary phenomenon, bubbling away deep inside Jupiter's core.
So basically we are creating a little planet interior inside our laboratory.
Marius Mio and his team at the National Ignition Facility conducted a pretty crazy experiment. They fired lasers at a tiny target, which imitates the core of Jupiter. The lasers simulate the unfathomable pressures going on inside.
So this is the target that we put inside this target chamber. We fill a little portion inside this cone here with liquid hydrogen, about 20 millionths of a gram. And then we shine 80 laser beams from the top and 80 laser beams from the bottom. So the power that we put in the lasers when we shine the laser onto the target is about 500 times the power that is used for the entire United States at a given moment.
5, 4, 3, 2, 1, shot.
Through the laser blast, the team observed this surreal change that takes place in the core of Jupiter.
At this time, the pressure got so high that the light is now reflecting off the shiny surface of the hydrogen. Hydrogen transforms from being transparent to opaque and then becomes a metal, like a shiny metal. If we were to go deep inside Jupiter, we would see a deep ocean of fluid, shiny metal.
And just like that, the planet completely messed with what's possible with the elements. It throws out the rulebook. On Jupiter, this metallic hydrogen makes up to potentially 50% of the planet's mass. And it's this huge liquid metal ocean that accounts for Jupiter's gigantic magnetic field. But that's not all. It also causes charged particles to leak out at its extremities, and it's this that causes the breathtaking auroras that outshine all the others in the solar system. So Jupiter's core is the main source of the auroras, but its moons also wanted to get in on the act, particularly one of the strangest moons in the solar system, Io. This moon is the most volcanically active in the solar system. Its spectacular volcanoes spew plumes up to 300 miles into the atmosphere, adding extra fuel to Jupiter's light show.
So we see Jupiter in the middle, but around Jupiter we see the moons, Io, Europa, Ganymede, Callisto. The gases that come from Io become trapped in the magnetic field, and they become accelerated to very high energies.
These trapped charged particles get dragged towards Jupiter's poles by its all-encompassing magnetosphere.
Energetic charged particles come in, bombard the atmosphere, make it glow. And then we're seeing this glow in the atmosphere of Jupiter.
So the combination of the gigantic magnetosphere, its supercharged liquid metal core, and unique moons create these breathtaking aurorae. But astrophysicists were still puzzled by one thing. Why do these aurorae light up and flash in semi-regular patterns, pulsing in this extremely bizarre way? It took a team at UCL to crack the case. In the time they watched the auroras, they found that they pulsed every 27 minutes. By closely analysing the data sent back from Juno and the European Space Agency telescope XMM Newton, they came to the conclusion that periodic vibrations crashed across the magnetosphere, causing waves of plasma to send heavy ion particles surfing across the magnetic field toward Jupiter. But the mystery isn't over. Just what causes these vibrations? What determines the pattern of these pulses? And why does Jupiter randomly decide on these rhythmic, regular intervals? This is just the beginning of our learning about Jupiter's auroras. And that's just the start of a wider search. There are more like them across the galaxy, waiting to be explored.
As the young Jupiter circles the Sun, it clears a path through the gas cloud that envelops the early solar system. But that process causes it to do something alarming. Jupiter begins to spiral inwards, plowing straight through the region of space that would become the asteroid belt.
When the young Jupiter moves through the primordial asteroid belt, things get scattered around, things get gravitationally deflected, and as a consequence of all of this gravitational interaction, more than 99% of the original mass that was there is basically now gone.
The
asteroid belt has been disrupted over time by the movement of the giant planets. And this has acted to throw material from the asteroid belt out of the asteroid belt into the outer solar system.
These protoplanetary cores, like Ceres, were never able to graduate to full-fledged planets because there was just not enough material in the orbital neighborhood.
When Jupiter passed through the primordial asteroid belt, it starved Ceres of material, halting its growth. And the dwarf planet was condemned to live out its life as a cold, barren rock. But Ceres isn't the only world in our solar system whose development was cut short. Mars would suffer a similar fate at the hands of Jupiter. After marauding through what would become the asteroid belt, Jupiter enters the region of space where Mars is forming. Continuing its journey, spiraling towards the sun. As Jupiter bulldozes inwards, its immense gravity scatters material in all directions. Some is sent careering into the sun. And some is thrown out into interstellar space.
It is because of the gravitational clearing of this neighborhood by Jupiter that Mars was unable to grow to more than 10% of that of the Earth. This is why Mars is small.
And by clearing material out of the inner solar system, the giant planet may also have prevented the formation of the super-Earths we see in other systems. And if it had continued moving inward, our planet too might never have formed. But then, just as it looks like Jupiter will sweep everything away, the giant planet stops in its tracks. Because in the shadows of the outer solar system, another planet is forming. The solar system's second gas giant, Saturn. And its arrival changes everything.
As Jupiter moved inwards, Saturn moved inwards and caught up to Jupiter's orbit. When this happened, the two locked into a special configuration known as a mean motion resonance. This is where the planets begin to interact gravitationally in a very coherent manner. And now, locked as a unit, the two reversed their migration course and moved back out.
Saturn caused Jupiter to retreat. Leaving behind just enough material from which the inner planets could form. Mercury, Venus, and our home.
Earth is in exactly the right location to provide the environment for life to develop. So if Jupiter had moved around even more, who knows? Maybe life never would have developed in the solar system as we know it.
And as its voyage across the solar system draws to a close, Jupiter helps to provide our living world with its most precious ingredient. Today, 2/3 of our planet's surface is covered by ocean. More than 1.3 billion cubic kilometers of water. Each drop teeming with life.
One of the big questions about the evolution of our solar system is, how did we get water here on this planet?
So we think that the inner planets didn't naturally form with a lot of water. Water is primarily in the outer solar system. But if you end up having Jupiter and Saturn moving outwards, then that is able to suddenly deliver more water into the inner solar system.
Locked in a gravitational dance with Saturn, Jupiter moves back through the asteroid belt. And as it does so, water-rich material is flung inward, where it is incorporated into the growing terrestrial worlds.
So the movement of the giant planets have actually played an important role in the delivery of water to the inner solar system.
In a sense, it is Jupiter's outwards motion through the asteroid belt that we have to thank for the delivery of water to the surface of the Earth. The Earth would be quite a different planet if not for Jupiter's primordial dance.